Welcome to Eager Space. One of my viewers asked this question recently. Could you discuss NASA's nuclear thermal propulsion project? At what payload/delta V does it become cheaper or easier than chemical rockets? Nuclear thermal rockets have been a perennial topic for years, starting when the NERVA rocket engine program was canceled back in 1973. There are always advocates trying to bring them back. But it turns out that, unless there are significant technological breakthroughs, nuclear thermal rockets are mostly pointless. They aren't worth developing. To understand why involves a bit of explanation. We'll start by comparing chemical rockets to nuclear thermal ones. Chemical rockets are very simple conceptually. You have tanks of propellant with a fuel like liquid hydrogen and an oxidizer like liquid oxygen. You have a way to move those propellants into a combustion chamber, and that's where you burn them. Fire makes things hot, and the products of the combustion exit the nozzle at high speed. We call that speed the exhaust velocity. If we take the exhaust velocity and divide it by the gravitational constant, we get what is known as the specific impulse of the engine. I have a whole talk about specific impulse. The simplest way to think about it is that it's like the fuel economy of a car. It tells you how much useful rocket stuff you can do with a given amount of fuel. And like fuel economy in a car, higher specific impulse is generally better. A nuclear thermal rocket doesn't use chemical combustion, and therefore you don't need any liquid oxygen around. Instead, it fills a heating area with nuclear fuel rods or spheres, creating a small nuclear reactor. Turn it on and pump liquid hydrogen through it, and the reactor heats up the hydrogen a lot, and it exits the nozzle at high speed. A much higher speed than the chemical rocket because hydrogen is very light. That gives us a very high specific impulse, around double what you can get with chemical rockets. That is why they are talked about so breathlessly. Double the specific impulse would be transformational, all other things being equal. The reality is that nuclear thermal advocates focus on the specific impulse and ignore other issues. To explore that, let's build our own nuclear rocket and compare it to a chemical one. This is going to be a level 1 analysis. It's going to give us answers that are mostly correct, but not precise. We'll be looking at an upper stage that has been flying for decades, the Centaur 3. It's currently flying on the last few Atlas V rockets. It is powered by the RL-10 engine, which has been flying pretty much forever. When looking at a rocket stage, we want to know what it can do with a specific payload. We use a measure known as delta V, which is just a measure of work. Rockets are actually pretty simple devices. To figure out the delta V, we need to know a few things: the specific impulse of the engine, the mass of the rocket when it is empty, including the payload, the amount of propellant, and the wet mass when the rocket is full of propellants. The specific impulse of the highest performing RL-10 is 465, the empty mass with an 8-ton payload is 10.2 tons, and the wet mass with 20.8 tons of propellant is 31 tons. Toss that into the rocket equation, and we get a delta V of 5,060 meters per second. If you want more details on the rocket equation and how it works, here's the video for you. Let's use that same Centaur 3 stage, but replace the chemical engine with a nuclear thermal engine, an engine named the Enhanced Simple Nuclear Rocket Engine. I chose that engine because it was designed to give the same amount of thrust as the RL-10 engine. It has a theoretical specific impulse of 906. No actual nuclear thermal engines have been built since the NERVA project in the 1970s. The engine mass is much heavier than the RL-10, so the empty mass is 3 tons higher, up to 13.2 tons. The propellant mass is 4.3 tons, and the wet mass is therefore 17.5 tons. Plug that into the rocket equation, and it spits out 2,500 meters per second of delta V. Wait a minute, it has twice the specific impulse, but ends up with only half the delta V? Shouldn't it have double the delta V? This is why you need to look at the values you get with a specific stage rather than just looking at the specific impulse. The problem is one of density. The RL-10 uses roughly a quarter of its propellant volume to store 17.6 tons of liquid oxygen. This is possible because liquid oxygen is very dense, packing 1,141 kilograms of mass into each cubic meter of volume. The density of liquid hydrogen is 70 kilograms per cubic meter, 1/16 that of liquid oxygen. That means that the liquid hydrogen tank is roughly 3 times the volume of the liquid oxygen tank, but carries less than 20% of the mass of the liquid oxygen. When we switch over to the nuclear engine, we'll fill that oxygen tank with liquid hydrogen, but we can only stuff in a little over a ton. That's why the delta V is so low. There's not much propellant. This isn't really a fair comparison. We need a stage with bigger tanks. We're going to substitute the much larger Centaur 5 that flies on ULA's Vulcan rocket. It carries 2.5 times the amount of propellant as the Centaur 3. I'm going to assume the mass of this larger stage without the engine is double that of the Centaur 3, and that gives us an empty mass of 15.1 tons. We now get 10.7 tons of propellant and a wet mass of 25.8 tons. Run that through the rocket equation, and we get a delta V of 4,750 meters per second. We're getting closer, but it's still less than the chemical rocket. In summary, the Centaur 3 tanks with an RL-10 give 5,060 meters per second. If we go up to the Centaur 5 size tank, the SNRE Enhanced gets 4,750 meters per second. Less than the RL-10 stage, but note that it's about 17% lighter in total wet mass. Bump up the size of the tanks so they have an equivalent wet mass, and we end up with these numbers. The nuclear model gets 5,950 meters per second of delta V, beating the RL-10 model by 17%. That's a relatively small difference, but it's hard to get delta V gains when the numbers are high, so this might be useful. I do have a few concerns with this model. First, this is a physically big stage. It may not fit on some launch platforms, or it may require modifications. With the exception of the NERVA nuclear thermal engines from the 1970s, none of these engines have been built. That means the specific impulse and engine weight are estimates. Specific impulse depends on the temperature in the reactor, and high temps may be hard to achieve in reality. We all know that pretty much everything in spaceflight world ends up weighing more than it is projected to weigh. Miss the specific impulse or weight targets, and that will eat into the advantage of the nuclear thermal engine. Nuclear thermal engines require shielding because they are radioactive during and after operation. The stage might require more shielding than what is accounted for in the engine design, and that will also eat into the advantage of the nuclear thermal engine. In other words, the NTR advantages in the model might not exist. What does the overall picture look like? The NTR wins the delta V battle. It produces about 17% more delta V for a given launch mass, or it can produce the same delta V with a smaller launch mass. It is, however, a much bigger stage. You can buy an RL-10 off the shelf from Aerojet Rocketdyne for something like $10 million, while your nuclear rocket engine will probably take billions to develop, and it will never be a cheap engine. The RL-10 uses liquid hydrogen and liquid oxygen, and the nuclear rocket uses enriched uranium. Some designs use weapons-grade uranium, which is mostly considered a non-starter these days. Some designs use less enriched uranium, which can only be used to make poorly performing bombs. There are a ton of hoops to jump through to work with nuclear materials in the US, and that increases the development cost significantly. Not to mention the approval process for launch and the pushback you will get. The RL-10 is not radioactive, and after startup, the nuclear rocket is radioactive as hell. The RL-10 has flown for many, many years and is hugely reliable, and the reliability of the nuclear rocket is unknown. It's not looking great for the nuclear thermal rocket. There's also the problem of testing. Chemical rockets are easy to test. You need a place that is remote enough to do the testing, and that's about it. NASA has test sites that you can lease, and SpaceX, Blue Origin, and others own and operate their own test sites. Back when NERVA was being developed, they just tested engines out in the open air. The exhaust is mostly non-radioactive hydrogen, until something goes wrong with the engine test, and then it spews radioactive material all over the test site. They operated out of a site known as Jackass Flats in Nevada. After test firings, the engines were returned to the main facility to be disassembled using remote manipulators to protect the operators from the radiation of the engine, the same sort of precautions used in nuclear reactor reprocessing. The approach used on Nerva is not environmentally viable in today's world. There have been other proposed ways of testing nuclear thermal engines. This one is known as subsurface active filtering of exhaust. You drill an 8-foot hole 1,200 feet deep into the earth and erect a sealed building over the hole. You then test your engine while spraying water into the hot exhaust. The combustion products would be cooled and trapped in the hole and would later be scrubbed to remove any harmful exhaust particles. You are then left with a highly radioactive engine inside a radioactive building. I'm not sure what you'd do then. This whole discussion would have been easier if there were a real-world NTR stage with known numbers that could be compared to chemical stages. This brings us to the Demonstration Rocket for Agile Cislunar Operations, or Draco. It was started by DARPA, the Defense Advanced Research Projects Agency, in 2021, with awards to General Atomics, Blue Origin, and Lockheed Martin for conceptual designs. Then, in 2023, NASA joined the Draco project. NASA already had their own demonstration project known as Space Nuclear Power and Propulsion, which I honestly think was more ambitious than Draco, but I haven't heard anything about the propulsion part since NASA joined Draco. Unfortunately, in January of 2025, the planned 2027 launch date was placed on indefinite hold due to the complexity of testing the nuclear engine on the ground and an unresolved design for the propulsion system. The project was not included in the 2026 NASA budget request, and in June of 2025, DARPA announced a termination of the program based on an assessment that the costs no longer matched the benefits, due to decreasing launch costs and a new analysis of the performance benefits. Remember that the real benefit of the nuclear stage was that it was a little lighter and therefore cheaper to launch than the chemical stage, but with launch costs going down, that isn't much of a benefit in the real world. The information from the Draco program was supposedly transferred to NASA, but I wasn't able to find any details of nuclear projects in the 2026 NASA fundings data, nor any updated status of the pre-Draco NASA project. I did hear from one person who says that NASA is still working on it. Nuclear thermal rockets sound great. Unfortunately, even in the best cases, the benefits do not outweigh the disadvantages, and they are therefore mostly pointless. For a look at some wilder nuclear concepts, I have a series of videos called Crazy Nuclear Rocket Engines. And that's all for this video. Today's song is Block Rockin' Beats by the Chemical Brothers from their 1997 album Dig Your Own Hole.